In section 5.1, we talked about estimating areas. Now I want to make it formal and also calculate exactly, look at the limit process and how you get exact areas underneath curves. So first we make a definition so we have some words to use to talk about what we're doing. So this is the definition of the definite integral. So definition. Given a function f of x defined on the interval a, b, we define the definite integral as follows. The integral from a to b of f of x dx. The way I read that is the integral from a to b of f of x dx. That the symbol is the integral symbol. Starting point, so the lower end, the starting point and the ending point of your interval a to b. This is the function that's being integrated, and this is, well, as you'll see as we look at this, the dx essentially is like a little bit of thickness. When you think about the pictures that we drew before, where we had our function and we cut the interval up into a bunch of little pieces, and we had a width times a height, right? That's kind of what this looks like. The f of x is telling you the height. The dx is a really thin, little small number for the width. But anyway, this definite integral is, this is how we define it, the limit as n goes to infinity of the sum, I equals 1 to n, of f of x I star times delta x, where all these symbols mean the same as they did in section 5.1, where delta x is b minus a over n, so the total length of the interval divided by how many pieces you're chopping it into, and xi star is a point in the ith subinterval. Right? That is, if you're going from A to B and you've cut it into so many pieces, this first subinterval we chose a point to figure out the height. That's x1 star, and then in the next interval we chose a point. That's x2 star, and so on. That in each of the n subintervals that you've chopped this into, you choose a point to plug into your function to figure out a height. You multiply it by a little width. So what I was saying is dx is playing the role of the width. Because we're taking a limit as n goes to infinity, delta x is going to be getting very small as n goes to infinity, because b minus a is a fixed length divided by a bigger and bigger number. So this is getting very small. So that delta x is really turning into this dx. I think of this as just a height times a very tiny little bit of width, and you add all those up. It's almost like I'm saying just that much times almost nothing of a width, and times the next one almost nothing of a width. They get really, really skinny, but you add enough of them up to generate the whole area. Now, this part of it, just in itself, whoops, that goes all the way up to the delta x there. This is what's called a Riemann sum. R-I-E-M-A-N-N. After the guy that essentially developed this process. And so the definite integral is the limit of the Riemann sums. The Riemann sums are the estimate, and you take higher and higher number of subintervals to get better and better estimates, and you take the limit to get the definite integral. Something to notice here. F of x does not have to be positive. If it is positive, then this notion of using it to calculate area is definitely um, definitely good and what we were talking about before. But it doesn't have to be. And in the event that it's not, then what's happening is something that's looking like this, where you've got a function that might be positive for a while, might be negative for a while. You've got your interval from A to B, and you've got your subintervals here, whatever. And, you know, for each, I'll just use right-hand endpoints for the sake of argument here. You know, for each interval, I'm picking a point, plugging it into the function, multiplying by the width. Taking a point, plugging it into the function, multiplying by the width. Plugging into the function, multiply by the width, and so on. There we go, all the way across. Now, over here, what just happened? Sorry. Over here, the height, the function value is positive, and the width is positive. So this is giving us some. When I look at the sum here, this sum part, that this first rectangle is giving us a positive contribution to that sum. Likewise here, with this being positive, just barely, but still that's positive. This one here with a negative value, this is essentially subtracting off from the sum. This one's negative, this one's negative, this one's negative. This one's positive, this one's positive, positive, positive. The delta x is essentially always positive if you're integrating from A to B. It'll turn out later we're going to go from B to A and then the delta x is negative. But for now we're integrating from left to right, so the delta x is always positive. The function might be positive or negative. Now this isn't actually calculating area, since it's a signed area or a net area. But it does make some sense in that if you think about one of the things we did in 5.1, it was if the function was telling us velocity, then this calculating of the area was somehow giving us distance traveled. Well, if the velocity is positive for a while and then negative for a while, the negative velocity means you're actually going backwards. So the net distance traveled is actually less. So it makes some sense that we should be subtracting off through those sections. Anyway, whether the function is positive or negative is irrelevant when it comes to what the definition is. Just take the interval from A to B, cut it up into n pieces, pick one point in each interval to plug into your function, take that height times delta x, add them all up, take the limit as n goes to infinity. Okay? And that's what we call the definite integral. Now there's two theorems I want to get out here before we actually do some calculating. First theorem says that if f of x is continuous on the interval a to b, or has only finitely many jump discontinuities, what do I mean by jump discontinuity? The function goes like that there's a left-hand limit and there's a right-hand limit at the point of discontinuity. There's not an asymptote, there's not any sufficiently squiggly stuff. It just goes left and right-hand limits exist but are not equal to each other. So that only happens finitely many times. Then f of x is integrable on a to b. And it occurs to me I didn't mention what the word integrable means. I defined the definite integral up above, right here. All right, this is the definite integral. And the thing is, if this limit exists, we say that the function is integrable on that interval. Right? It has an integral, so it is integrable. So anyway, sometimes that limit won't exist. Sometimes you'll try to take the limit and you'll get infinity or something weird will happen. But generally, if you got a nice function, you got a finite length interval, then the function is integrable. Okay. And lastly, for now, that's one more theorem. I want to say if f is integrable, essentially the theorem is bigger than what I'm going to state. Essentially, um, if it's integrable, then it doesn't matter how you choose your xi stars. So essentially, though, there's one set of xi stars that are generally easier to work with, and that's the right-hand endpoints. So it's integrable. If it's integrable on a to b, then the definite integral f of x dx is equal to, and I'm just setting up the same thing that we had before. The limit as x goes to infinity of, sorry, the sum, so the limit as n goes to infinity, the sum I equals 1 to n of f of, and instead of an xi star here, I'm going to write a plus I delta x times delta x where, of course, delta x equals b minus a over n. Right? So I'm just choosing which xi stars I'm using. And that formula right there, that a plus I delta x, comes from, if you look at the interval from a to b, oops, I don't know why I keep doing that, but from a to b, you cut it up into n pieces. Each width here is delta x. So this first spot, this first right-hand endpoint, is a plus 1 times delta x. And in order to get to this x value, you got to start at a and move over 2 delta x's. So that's a plus 2 delta x. And this would be a plus 3 delta x, and so on. Right? So a plus I delta x is, you're starting at a and you're moving over I times delta x. Well, that gets you over to what we're calling x of I. So this is just saying I'm going to just use right-hand endpoints. It's generally pretty easy to calculate. You get this nice formula for what the xi star is. So anyway, we will move on to actually doing some calculations in the next video.